Problems involving equilibrium involving charged particles are generally set up the way you see. You're given the value of two charges, in this case both positive, a 3.5 nanocoulomb and a 5 nanocoulomb charge, and you're given the distance between them, in this case 0.4 meters. We're going to place a third charge, in this case negative 6 nanocoulomb, somewhere in association with the other two particles. And the question is, where do I have to place that charge so that on it the net force is 0? Well, if we think back to our ideas on equilibrium, in order to have net force, the sum of all the forces, to have net force equals 0, the sum of all forces must equal 0. So for my net force, the forces I have would be between, we're going to go ahead and call this particle A, and we'll call that one B, and C. Between A and B, that force, plus B and C, has to sum to 0. So the first thing I'll need to do is find the force acting between particles A and B, find the force acting between particles B and C, assess direction, in other words, right, left, positive x-axis, negative x-axis, etc., etc., and then set them equal to each other. Because another way to write this is AB is negative BC. So if I set my forces equal to each other, that's a very quick way to go about solving for equilibrium. And we did that when we worked with equilibrium with boxes and things like that before. So the first step, of course, is to solve then for the different force pairs, or should I say the forces for the different charge pairs. For the AB force, I have a 3.5 nanocoulomb, which is times 10 to the minus 9 coulomb. I have my minus 6 times 10 to the minus 9, or negative 6 nanocoulomb. And notice I'm leaving the coulombs off for right now. I can't forget about good old K. He has to be there, for at least for right this minute. And my distance, I don't know. That's what I'm looking for. So for right now, I'm just going to go ahead and call it X. Now for my BC pair, I'll still have K involved. But my new pair of charges is the negative 6 times 10 to the minus 9 coulomb, and the charge at the end, which was a positive 5 times 10 to the minus 9 coulomb. And the distance, well, that's kind of a kicker. How do I assess the distance? Well, I can't assess it, I can't call a different variable necessarily. That's actually going to put two variables in my formula. But I do know the total span between the particles is 4.4 meters. So 0.4 meters minus the distance between particle A and B would actually equal the distance between particles B and C. So by writing the distance in this fashion, I still only have one variable in my formula for position, and now I'm in a pretty good situation to get this set up. Set my forces equal to each other, so I have K, negative 6 times 10 to the minus 9 coulomb, and positive 3.5 times 10 to the minus 9 coulomb over x squared is K. What do I have? Negative 6 times 10 to the 9th coulomb, and 5 times 10 to the 9, and x minus, or excuse me, 0.4 minus x squared. A little bit of cross multiplication, and obviously these numbers are starting to get pretty big, so I'm going to go back to the nanocoulomb notation, but remember what it's actually standing for, okay? K, negative 6 nanocoulomb, 3.5 nanocoulomb, times 0.4 minus x squared is x squared times K times negative 6 nanocoulomb, and, oh God, I'm going to have to try and squeeze them in there, 5 nanocoulomb. First thing to do, start doing some canceling. I can cancel K, it's on both sides. negative 6 nanocoulomb. It's on both sides. Now I have 3.5 nanocoulomb times 0.4 minus x squared is x squared times 5 nanocoulomb. Well, I could go ahead and make this a quadratic and go through all that 9 yards, or I could make my life a lot easier. Take the square root of both sides. Square root of 3.5 nanocoulomb times 0.4 minus x is x times square root of 5 nanocoulomb. That's a lot simpler than working with a quadratic. Now it's just a matter of doing a little bit of algebra. Square root of 3.5 nanocoulomb times 0.4 minus square root of 3.5 nanocoulomb times x is x times square root of 5 nanocoulomb. In other words, just go ahead, isolate, and solve for x at this point. And when you do, x winds up being 0.18 meters. But now we have to ask ourselves, from which particle was that 0.18 measured? That 0.18 distance was measured in association with the 3.5 nanocoulomb particle. So the negative 6 nanocoulomb charge needs to be 0.18 meters from the 3.5 nanocoulomb charge, or what is it, 0.22 meters from the 5 nanocoulomb charge. And at that position, my little negative 6 nanocoulomb charge is subject to zero net force. So, first off, sketch your situation, as always. Think about our idea of net force and how we can set our forces equal to each other in order to solve, then, for perhaps an unknown in the equation, in this case, the idea of distance. Set up Coulomb's law for one charge pair, identifying our distance variable as x. Set up Coulomb's law for the second charge pair, using the total distance to help define the distance between our target charge and the other member of our charge pair. Go through all the horrible algebra. Expand out your formulas for Coulomb's law. Do your cross multiplication. Once you get to this step, make it easy on yourself and just take the square root of each side. And then it's a quick matter of going from this step to solving for x.